integers and rationals. So, so far we have defined actually only what he calls natural numbers, the set consisting 0, 1, 2, etc. In chapter 2, we build up most of the basic properties of natural number system. But we have reached the limits of what one can do with just addition and multiplication. We would like to introduce a new operation that of subtraction. But to do that properly, we will have to pass from the natural number system to a larger number system, that of the integers. Integers will informally, the integers are what you get by subtracting natural numbers. So that is kind of the normal approach, however. For instance, 3 minus 5 should be an integer, as should 6 minus 2. This is not a complete definition of the integers because it doesn't say when the differences are equal. For instance, we should know why 3 minus 5 is equal to 2 minus 4, but is not equal to 1 minus 6, and B, it doesn't. See how to arithmetic on these differences, how to do. How does 1 add 3 minus 5 to 6 minus 2? Furthermore, this definition is circular because it requires a notion of subtraction, which we can only adequately define once the integers are constructed. Fortunately, because of our prior experience with integers, we know what the answers to these questions should be. To answer A, so can you see he is defining, because for what you asked, he is defining the integers using the difference from what we know. Background comes from our knowledge. To answer A, we know from our advanced knowledge in algebra. A minus is not advanced. A minus B equals C minus D happens exactly when A plus D is equal to C plus B. Thinking that way is a very sharp thing somehow. Because I myself was wondering how on earth he is going to define integers. So he has thought of this. This is a very remarkable thought. Exactly when A plus D is equal to C plus B, so we can characterize equality of differences using only the concept of addition. Similarly, to answer B, we know from algebra that A minus B plus C minus D is A plus C minus B plus D, and that A minus B times C minus C D is equal to this thing, usual product. So we will take the advantage of our foreknowledge by building all this into the definition of the integers, as we shall do shortly. We still have to resolve A. To get around this problem, we will use the following workaround. We will temporarily write integers not as a difference A minus B, but instead we now take A long letter B, long subtraction. No? How do we call it?
Long dash.
Long dash. Okay. That's a clever thing actually. Where the long dash is a meaningless placeholder, similar to the comma in the Cartesian coordinate system. Well, I don't think they are similar. No? Comma is, I guess. I don't believe that it is similar. Anyway, it doesn't matter. That's what he says, no notation xy for the points in the plane. Later, when we define subtraction, we will see that you said long dash, because I had to have some word to read, no? We see that A long dash B is in fact equal to A minus B, and so we can discard the notation long dash. Here he says he can discard the notation long dash, but he doesn't want to discuss plus plus. No? It is only needed right now to avoid circularity. These devices are similar to the scaffolding used to construct a building. They are temporarily essential to make sure the building is built correctly, but once the building is completed, they are thrown away and never used again. But other people use them again, to build another house. Anyway, so you got the message, no? He is using, it's like when you are building a house or a building, you have bunch of scaffolding, pipes, this and that around. But once the house is built, they are thrown away from that place, as he is saying, taken to another place to build the next house. So similarly, we can, after everything is over, we can throw away the long dash and come to the subtraction sign, negative sign. This may seem unnecessarily complicated in order to define something that we already are very familiar with. But we will use this device again to construct the rationals, and knowing these kinds of constructions will be very helpful in later chapters. Clever guy. Integers. An integer is an expression for the time being of the form a ln dash b. That's the definition of how this is provisionally, for the time being, temporarily. An integer is an expression of the form a ln dash b, where a and b are natural number. We know natural number, we don't know the meaning of ln dash. So that's just the way of writing. Two integers are considered to be equal. Now a ln dash b and c ln dash d are integers. We don't know the meaning of ln dash. If and only if, however, a plus b is equal to c plus b. Now we know the meaning indirectly. You cannot say, we cannot say what is a ln dash b means, but a ln dash b and c ln dash d are equal if and only if a plus d is equal to c plus b. That side we know the meaning, because a and b are natural numbers. We let z to denote the set of all integers. That is, he said this for the time being. For the time being, he said this a ln dash b, ab belongs to n. That's the definition of, he said, provisionally. Thus, for instance, 3 ln dash b is an integer and is equal to 2 minus 2 ln dash b, because 3 plus 4 is equal to 2 plus 5. When you take the 3 ln dash b alone, we don't understand what it means. But we know it is equal to that because of this. On the other hand, 3 ln dash b is not equal to 2 ln dash 3, because 3 plus 3 is not equal to 2 plus 5. This notation is strange looking and has a few deficiencies. For instance, 3 is not yet an integer. 3 is a good natural number but not an integer yet, because it is not of the form a minus b, exclamation mark, surprise. We will rectify these problems later. We have to check that this is a legitimate notion of equality, because mathematically it should be well defined. Yes.
It's not the form, you can write 3 as a subtraction of 2 natural numbers. That's what I was going to ask. But we haven't defined that long dash notation.
3 is when because now you are thinking 3 is equal to 5 minus 2. You cannot write that for the time being. Here, integers are this. A ln dash b, a b are integers. 3, of course, to us 3 is an integer, but for our class 3 is a natural number, but not an integer. I mean, provisionally, as of now. We need to verify the reflexivity, symmetry, transitivity and substitution axioms. We leave reflexivity and symmetry to exercise 4.1.1 and instead verify the transitivity axiom. Suppose we know that a ln dash b is equal to c ln dash b and c ln dash d equals to e ln dash f. Then we have a plus d is equal to c plus b and c plus f equals to d plus e. Then I guess he adds both of them together, no? A plus d plus c plus f, c plus b plus d plus a. Then you have c d CD in both sides. You have the cancellation law we proved, no, in about natural numbers. Then you can cancel. Maybe proportion 2.26 is the cancellation law. Then you get A plus F is equal to B plus C. Kuta, you follow? That is A, by definition, A ln dash B is equal to E ln dash F. Thus the cancellation law was needed to make sure that our notion of equality is sound. As for the substitution axiom, we cannot verify it at this stage because we have not yet defined any operations on the integers. Without having any integers, we cannot do anything. However, when we do define our basic operations on the integers such as addition, multiplication and order, we will have to verify the substitution axiom at that time in order to ensure that the definition is valid. We will only need to do this for the basic operations. More advanced operations on the integers such as exponentiation will be defined in terms of the basic ones, and so we do not need to re-verify the substitution axiom for the advanced operations, because when we do the basic ones, big ones are depending on the basic ones. No? Now we define two basic arithmetic operations on integers, addition and multiplication. Now we know any integers of the form a ln dash b, a and b are integers. We have no idea whatsoever other than a minus b is a ln dash b is equal to c ln dash d if and only if a plus d is equal to b plus c. That's all we know of. Okay, the sum of two integers a ln dash b plus c ln dash d is defined by the formula, expected formula. A plus c is like complex number addition, no? You add real parts, imaginary parts separately. Similarly here, the product of two integers is defined again. When you multiply this thing, you get AC plus BT positive, then AD, BC negative, so he has put them together. So this is the definition, that's why he has this definition. It's not exactly an equal sign, defined to be equal, that's what it means over there. Thus, for instance, 3 minus 3 ln dash b, 5 plus 1 ln dash c, 4 is equal to 4 minus 4 ln dash 9. There is, however, one thing we have to check before we can accept these definitions. We have to check that if we replace one of the integers by an equal integer, that the sum or product does not change. If it is well defined, we must be able to do so. For instance, 3 ln dash 5 is equal to 2 ln dash 4. So 3 ln dash 5 plus 1 ln dash 4 out to have the same value as 2 ln dash 4 plus 1 ln dash 4. Otherwise, this would not give a consistent definition of addition. Fortunately, this is the case. Now he is proving it for this thing. I mean, we can go through it, but you have to do it by your hand to make sure that that's how mathematics get to you like that. If you want to learn to swim, you have to jump to a swimming pool. Otherwise, you will never learn. Addition and multiplication are well defined. He says, let a b, a dash b dash c d be natural numbers. If a minus a ln dash b is equal to a dash minus a dash ln dash b dash, then a minus a ln dash b plus c ln dash d is equal to a ln dash b dash plus c ln dash d. Similarly for multiplication. Again from the other side, c minus d, c ln dash d plus a ln dash b is equal to c ln dash d plus a ln dash ln dash with an a dash, ln dash, b dash, so many dashes. So whether you get it front or back, can it? left side or right side, you have to end up with the same answer. Thus addition and multiplication are well-defined operations. Equal inputs give equal outputs. Before we prove this thing, actually I also did not think that it will work out. Because this is something you don't expect, no? Anyway, to prove that A ln dash B plus C ln dash D is equal to A dash ln dash B dash plus C ln dash D, we evaluate both sides. When you evaluate A plus C ln dash B plus D, you get and A dash plus C ln dash B dash plus D. So we evaluate both sides of this thing. We need to A plus C plus B dash plus D. No? You understand what I am saying? Here now, we want to prove that these two are the same because A minus B and A. I got saying minus is easy, but it's not minus. Anyway, A log minus B is equal to A dash log minus B dash, no? So this is equivalent to A plus D minus, B plus C. So we want to prove this one, and again this is A plus C minus B plus D. That one is A plus C minus B dash plus D. Then if you want to say that they are the same, A plus C plus B dash plus D must be equal to A dash plus C plus B plus D. But since A minus B is equal to A dash minus B dash, I am saying minus, which is not correct. We have A plus B dash is equal to A dash plus B. And so by adding C plus D to both sides, we obtain the claim. Here, if you try to do what have to be happen, you get it. That's all. Now we show that A minus B times C minus D. I will say minus, otherwise I will get time. A minus B times C minus D is equal to A dash minus B dash and C minus D. Both sides evaluate. Here you get AC plus BD ln dash minus AD plus BC. Over there you get A dash C plus B dash D minus A dash D plus B dash C. So then these two must be the same. Then you get AC plus BD plus A dash D plus B dash D. Right hand side A dash C plus B dash D plus AD plus BC. Puta, are you follow? But the left hand side factors C times A plus B dash, left hand side, plus D times B plus A dash plus B, while the right factors as right hand side factors as there on my right side, over there C times A dash plus B, C times, and D times B dash plus A. So he has written A plus B dash. Since A plus B dash is equal to A dash plus B, the two sides are equal. He says he is using what to happen. He knows what should be the case, and he is using that. So finally, it is the same. Anyway, it is good thing is that he thought of this way. I did not think at the beginning it will work out. If somebody came and told me, you define, on the way to define A minus B, then you define this symbol which does not have a meaning, But you say this one, if you write C longer line D, if they are equal, that means A plus D is equal to B plus C. From that, one cannot expect. Eventually, one would be able to define minus. So it is a clever thing. That's why I told you that some unsolved problems in mathematics, mathematicians are worried. Somebody man in the street will come up with a solution. It's genuine thinking. No? So this sort of thing is somebody may come, who knows? So that's why if you think that you yourself, you are young, now you are better than me, now you are not spoiled yet, no? You are not spoiled, so if you think about some problems, you may, I told you this 3n plus 1 problem the other day, no? So something like that, you may get the solution. I tried hard, no, didn't work. Now anyway, he has proved two sides are equal, so it is well defined. Now the integers n minus 0, because we haven't defined integers. No? Now we know the integers, we know natural numbers. We know natural numbers. Here we have this thing, natural numbers capital N. We have 0, 1, 2, 3, 4 like that. Oh, sorry. We have. Now, we want to embed this thing to this one, because we want every natural number to be an integer. So we want somehow it should go. The other day we talk about the isomorphism. We need some isomorphism, some kind of mapping, 1 to 1, 1 to, that these guys must live here. Yeah. So what do we, the integers n minus 0 behave in the same way as the natural numbers n. N minus 0 is an integer. It's not a natural number. However, he says the integers n minus 0 behave in the same way as the natural numbers n. Indeed, one can check n minus 0 plus n minus 0, though I am saying minus, you know what I mean. N plus n minus 0. And n minus 0 cross n minus 0 is n minus 0. Furthermore, n minus 0 is equal to n minus 0 if and only if n is equal to m. Now, he is showing a kind of isomorphism from here to there. The mathematical term for this is that there is an isomorphism between the natural numbers n and those integers of the form n minus 0. We are saying if you take an n here, n is matching to n minus 0, n goes. So this n and n minus 0, they behave the same way. Here, some groups isomorphism. I will explain the word isomorphism next day because I don't get the example right. Isomorphism is in two sets. When we say here these two are isomorphic, in one set some objects, in this case numbers, in the other set not the same thing, something else, but they both behave the same way. Now here you have n's here, n minus 0 here. They are not equal because this is a natural number. This one is no meaning yet. But over there, all we can do is addition and multiplication. For these operations, they behave the same way. Behavior of n and behavior of n minus 0 log minus 0, they are the same. That's what we have shown there. N minus 0 times m minus 0 is nm minus 0. So if you match n to n minus 0, fine. If let's call the map f. We have shown that what is you match fn is equal to n minus 0. This is the map. I should have had the next day I will bring a lesson 15 minutes group theory lesson to talk about n minus 0. So here he has shown f of n plus m is equal to fn plus fn, and f of nm is equal to fn times fn. So n plus m, n plus n with respect to addition, n plus m, both addition wise they are the same, multiplication wise they are the same, different objects. In group theory actually you get so many examples. One group has, let's say, let's say A, B, C, D, E, for instance. I will bring a good example next day. In another, this is G1, other group may be permutations. Permutation, you know, permutation means 1, 2, 3, 1 goes to say 2, 2 goes to 3. You know the word permutation, no? Actually, any group is isomorphic to some permutation group. That's the theorem. Any group, no matter what group you take, it is isomorphic to a group of permutations. But in this group, you don't have permutation. In this group, you have permutations. Behavior, identical. No difference. That's why we call it isomorphic. In analysis, we call it isometrically isomorphic. Isometric means distance. Distance wise also the same. So we cannot go that far today. The mathematical term for this is that there is an isomorphism between the natural numbers n and those integers of the form n minus 0. Exactly what I told you. Behavior of n and m and for addition and multiplication and behavior of n log dash 0 are the same. So that's why we say they are isomorphic. So we can think of n as inside here. N does not belong to this set, but n's image n minus 0 is in that set. So that's what he is doing. Thus we may identify the natural numbers with integers. Exactly what I am saying. In 3 lines, not equal. This does not affect our definition of addition or multiplication or equality, since they are consistent with each other. For instance, the natural number 3 is now considered to be the same as the integer 3 minus 0. Now you can say 3 is 3 minus 0. I mean log minus. However, 3 is not equal to 3 minus 0. You cannot say so. Thus, he has written 3 equals 3 minus 0. In particular, 0 is equal to 0 minus 0. Although he is writing actually, 0 is recognized as 0 minus 0 in that set, and 1 is equal to 1 minus 0. Of course, if we set n is equal to n minus 0, then it will also be equal to any other integer which is equal to n minus 0. For instance, 3 is equal not only to 3 minus 0 but also to 4 minus 1, etc., etc., etc. So, I wish he had not written 3 equals 3 minus 0. That's not a good thing, no, without writing, because here is one ring actually. This is a ring. You have seen the word ring here and there, no? This is a ring you can multiply and add. That is also a ring you can multiply and add. So, numbers, now here you have natural numbers, over there you have something called integers, you don't know what it means. You have A minus B, I mean A log minus B. So when as far as natural numbers are concerned, under this map, f of n plus n and fn plus ff are the same. Similarly, f of nm and fn ff are the same. So it's not a good thing that he wrote, but eventually maybe you may have to write. We can now define incrementation of integers by defining x plus plus by definition equal to x plus 1 for an integer x. This is of course consistent with our definition of the increment operation for natural numbers. However, this is no longer an important operation for us, as it has been superseded by the more general notion of addition. So, I mean, that's not important. It is superseded by the more general notion of addition. Now we consider some other basic operations on the integers. Negation. Now, these are the integers. You can add, you can multiply. They behave like, I mean, when it comes to the natural numbers, they also, I mean, on par with the behavior of integers, what he calls integers. If a minus b is an integer, we define the negation, negative a minus b, to be the integer b minus a. That's its definition. Negative a minus b, that's the definition. So we can talk negative a minus b is equal to b minus a. In particular, if n is equal to n minus 0 is a positive natural number, we can define its negation as 0 minus n. That's the that is the definition. For instance, negative 3 minus 5 is 5 minus 3. One can check this definition is well defined. See exercise 4.1.2. I mean, it is not the thing. Yeah. Over there. There is a little question somewhere. That's why I was checking. We can now show that the integers correspond exactly to what we expect. Trichotomy of integers. Now we are going to assume that we know integers. Integers are of this form. A and B are natural numbers, and we know how to add integers. We know how to subtract. Sorry, yeah, we know how to multiply integers. We know the negative of an integer. These are the things we know, and most importantly, natural number n and n minus 0, their behavior with regard to addition and multiplication are the same. The way n and m behave in the set n and the way n minus 0 and n minus 0 behave are the same. They are different looking. That's all. Trichotomy of integers. Let x be an integer, then exactly one of the following three statements is true. X is 0, x is equal to a positive natural number, or x is the negation minus n of a positive natural number. So you need to read them carefully, and you must be able to accept that without taking anything for granted, you are proving. That is important. Otherwise, just by reading won't help. First we show that at least one of ABC is true. We have done this sort of thing. And then at least one of them we have to do. At most one of them is also true, no? We want to say one is going to happen. Either x is 0, either x is equal to a positive natural number, n or x is the negation minus n of a positive natural number. These three. By definition, x is equal to a minus b for some natural numbers, a, b. You take x, you have to prove either x is 0, x is equal to the positive natural number n, or x is the negation minus n of a positive natural number n. You have to prove. And exactly one of them is going to happen. So here he is proving at least one of them is going to happen. Then he has to prove at most one of them is going to happen. That completes the proof of exactly one is going to happen. So he took we first saw that this thing by, he took a number x. X is of the form a log dash b, a and b are natural numbers, no? Any integer is of that form, no? So far we don't know the actual meaning of this long dash. We have three cases, a greater than b, a equals b, or a less than b. If now a and b are natural numbers, now we spend exactly one chapter to study natural numbers. If a greater than b, then a is equal to b plus c for some positive natural number c. That is actually the definition of a greater than b, if you recall it, which means that a minus b is equal to c minus 0. No? By definition. A equals b plus c, without writing on the board, here it is there, a equals b plus c, and they are the same. This means a plus 0 is equal to b plus c. That's what exactly it is. Which is b. B is what? B is x is equal to a positive natural number. We have shown a minus b, a can log minus b is equal to c minus 0. C minus 0 is exactly c, which is b. If a greater than b, we got b. If a is equal to b, then a minus b is equal to a minus a. A and b are same, no? In the place of b, you wrote a minus a is 0 minus 0. 0 minus 0 is actually 0, which is a. And if a less than b, then b greater than a. So b minus a is n for some natural number in my previous reasoning. Therefore, a minus b is some minus a. A minus b is minus of b minus a. So, in which case, so at least one of them is happening, we have proved now. Now we show that no more than one of A, B, C can hold at a time. So I will not go through the details. You can read it. So here what he is showing is this trichotomy of number. When you take any integer, either it is 0. You can go through the proof here. It's not difficult. Any integer is either 0 or it is. Now our definition is this, no funny thing. Either it is 0, either it is a positive natural number, or else it is a negative of a positive natural number. So that's what he is proving here. So we need to remember that the reason is after this first 5 chapters are over, you are not going to worry about them. You will say let x be a real integer, then you will say either x is 0 or x is positive or x is negative. You are going to say that. Now here you are proving actually that is the case. If n is a positive natural number, we call minus n a negative integer. Thus every integer is positive, 0 or negative, but not more than one of these at a time. Starting from chapter 6, you are not going to worry about what we are proving right now. You are going to take them for granted thereafter. But that's why you need to go through the proof carefully to make sure that, because after chapter 6, you are not going to wonder, oh, is that true, is that true? I mean, you can add, subtract, multiply, this and that you do as usual, like the way you did in A-level. One could well ask why we don't use lemma for 1.5. I mean, it is, if you are going to use that way to define, there will be, you can do it. He says it will be much messier. We now summarize the algebraic properties of the integers. Now, remember, integers are like this. And we know how to add, we know how to subtract, we don't know how to say x less than or equal to y, that kind of thing we don't know yet. But other things we know. So these are the results. The above set of 9 identities have a name. They are asserting that the integers form a commutative ring. Algebra commutative ring is a commutative part comes from 1, 2, 3, 4. Fifth one, xy equals yx. Product is, order is redundant. Product of two numbers, order redundant. That's why we say commutative rings. In algebra, commutative ring is a real big research area in rings. Some people say, what do you do? Oh, I am doing commutative rings. Somehow, I was very good in algebra, but somebody who like analysis, though analysis is difficult, will enjoy doing analysis. Algebra, I guess I shouldn't say, but not entertaining, I thought. I like to face the challenge. I may not be able to do it, but still, if one deleted the, identity xy equals yx, then they would only assert the integers form a ring. Ring means not the ring you put in the fingers. Notice that some of these identities are already proven for the natural numbers, but this does not automatically mean that they also hold for the integers. You can prove them actually, not difficult, because the integers are a larger set than the natural numbers. On the other hand, this proposition supersedes many of the propositions derived earlier for natural numbers. They supersedes, it's go to a higher level. There are two ways to prove these identities. The best way is you take xa minus b, yz minus d, then e minus f. But simplify both sides, you get the same thing. That's the best way to prove. So let's not think about it. But you should write it. He is doing it. No? X, y, z. First he multiply x comma y. X times y. X is a minus b, c minus d, then he get ac plus bd minus ad plus bc. Then he is multiplying by e minus f. He gets some answer for xy times z. Then similarly he is showing x times yz, and eventually he has got the same thing. So that's why they are the same. So it's a very elementary thing. You don't need the brain, but you have to sweat. We now define the operation of subtraction x minus y of two integers by the formula. Let's see whether this is right. You have given two integers, xy, not natural numbers. Now you want to define x minus y. We don't know x minus y, no. We have defined negative y, however. So he says x minus y is x plus minus y. Or a right hand side is integers, integer addition. You have to be careful. X minus y, now he is using the our minus sign, is x plus minus y. X minus y is defined to be x as an integer plus minus y as an integer. So here is the definition of x minus y. We do not need to verify the substitution axiom for this operation. He says since we have defined subtraction in terms of two other operations on integers, they are well defined. As a result, this is well defined, namely addition and negation, and we have already verified that those operations are well defined. We have done it. One easily can check now that, let's see whether this is correct, we can understand. Now that if a and b are natural numbers, Assume A and B are natural numbers. So A minus B, we know the meaning. A minus B, left hand side A minus B is, do we know the meaning? No. Did we learn how to subtract natural numbers? No, we don't. We didn't study. So A minus B, one can easily check now that I have a problem here somehow, it's kind of bothering me. A and B are natural numbers, then A minus B, since they are natural numbers, however they are integers. So here, though he wrote A minus B, here he has written, since A is identified with A minus 0, B is identified with B minus 0, that is that A minus B. You see what I am trying to say? Can you? Kind of confusing here. He is going to prove that for integers A minus B and A lone dash minus B are the same. He took two natural numbers, A, B. Here A lives in this one, B lives in this one also. For them, A minus B have a meaning. Though he says it is natural, though they are natural numbers, this means the difference between two. How can I say? I am confused with this. You have two natural numbers, you don't know how to subtract. One can easily check now that if A and B are natural numbers, then this thing happens. Since A and B are integers, A minus B has a meaning. A plus minus B. Over there he defined operation. We now define the operation of subtraction xy for two integers. X minus y is x plus minus y. So he defined that way, assuming that A and B are integers. No? A and B are integers. Then it is A plus minus B. However, since A, we know that A is a natural number, A is A minus 0 by this identification, and minus B is 0 minus B. But that is A minus B, A long dash minus B. Are you happy? I am not. I am kind of bothered about this. I spent several minutes, 3 days. I still have a kind of.
Yeah, because he gave the definition for two integers, but he has used the thing for two natural numbers.
Natural numbers. I am kind of bothered.
First of all, he should have known that the natural numbers are a subset of integers. No? Then it will be okay. He showed it first.
But let's, without worrying too much, we have to continue. Because for your analysis knowledge, it's not going to play any role. But for the construction, he took two natural numbers. So natural numbers are embedded in C. Then my problem is, he has written A minus B. No? How can we write for natural numbers A minus B? That is the problem.
He didn't say those are natural numbers, right?
A and B are natural numbers.
If simply we are
Can check his
Eh?
how can you check it? Because the definitions for the subtraction is for two integers.
Two integers. No?
Yeah, he's going to check whether
So how can you check with the definition doesn't match the domain of the A and B.
I mean, if A and B are integers, we can do that.
Now A and B are natural numbers. No?
That's the thing.
My problem is how can he write A minus B over there? If he writes, he can write using this embedding. Then that is not natural number subtraction. I am a little bit doubtful. Let's 4 people with me, 5 people, we should think about this. I have a question.